picture this, right? The glow of a monitor is literally the only light in the room. A single individual is just, sitting at a keyboard analyzing the cryptographic architecture of this massive, globally distributed financial system.
Well, it sounds exactly like the opening of a movie.
Right, but it's not a script. It's not speculative fiction. This is the actual true story of an ethical hacker named Gearhard Wagner.
Such a wild story.
It really is. So he was probing the Polygon network, which is a layer 2 scaling solution for Ethereum. We are talking about millions of dollars in cryptocurrency transactions happening every single day.
Just a massive amount of capital flowing through there.
Exactly. And buried under all these layers of complex smart contracts that manage the bridge between those networks, Wagner discovered this microscopic, almost invisible vulnerability, basically a double spend bug.
And I mean, in the architecture of digital finance, a double spend bug is, well, it represents the absolute collapse of the system's foundational logic.
Yeah, because you can't have fake money.
Right. Blockchain is built entirely on immutability. The whole idea is that a digital token can only exist in one place at one time. But Wagner found a flaw in the plasma bridge withdrawal process.
The withdrawal process, yeah.
He realized that if an attacker, manipulated the specific state changes during a transaction, they could submit a legitimate withdrawal request, right? And then before the system's internal ledger fully resolved that state, they could just submit it again.
Oh, wow.
And again.
Yeah.
The system's internal clock and validation checks were effectively completely out of sync with the cryptographic execution.
The math on this exploit is it's absolutely mind-blowing. This specific timing mismatch would have allowed an attacker to multiply their cryptocurrency withdrawals up to 233 times in a single sequence.
233 times.
It's crazy. To put that in perspective for you, a mere $4,500 deposit into the network could be instantly leveraged into a $1 million withdrawal. And if a malicious attacker started with, a slightly larger pool of capital, say like $3.8 million, they could have exploited this exact sequence to systematically drain up to $850 million from the Polygon network.
Almost $1 billion. Just gone.
Just gone. It would have been this catastrophic heist executed entirely in silence without a single physical trace, just from a laptop anywhere on the planet.
I think it really demonstrates a level of power that, fundamentally reshapes how we understand risk today. The ability to cripple a multi-million-dollar financial ecosystem, it doesn't require an army anymore. It just requires an internet connection and this incredibly deep understanding of system mechanics.
But, and here is where the story shifts from a potential disaster to an absolute masterclass in professional cybersecurity. Gearhard Wagner didn't drain the network.
Right, he wore the white hat.
Exactly. He didn't exploit those state changes for personal theft. Instead, he meticulously documented the cryptographic mismatch, packaged his proof of concept into this pristine, actionable report, and submitted it directly to Polygon's engineering team.
And they rewarded him for it.
Oh, they did. For his incredible technical skill and, honestly, his integrity, Polygon paid him a bug bounty reward of $2 million.
That is just incredible.
$2 million, completely legal, totally above board, which, brings us to the ultimate question for you listening right now. How do you actually build the foundational skills to hunt for these multi-million-dollar vulnerabilities?
Yeah, and more importantly, how do you translate a raw technical exploit into a professional report that an enterprise organization can actually use to patch their systems?
Exactly. So before we dive into the blueprint for building those exact skills, make sure you like, subscribe, and share this deep dive so you never miss the insider tips that could one day literally save your IT career.
Absolutely.
And be sure to direct your attention to the description below for access to additional resources you'll definitely find valuable. Because today we are going to equip you with the knowledge you need to navigate this incredibly high-stakes landscape.
Because, the line separating a lucrative, highly respected cybersecurity career from a devastating operational mistake is almost always drawn by the foundational methodology you apply before you ever launch a single packet across a network.
So true. So let's set the stage for today's mission. This is a special moment because this is the 14th and final deep dive in our 14-part series based on the textbook Hands-on Ethical Hacking and Network Defense, 4th edition, by Wilson, Simpson, and Antil.
The grand finale.
The grand finale. Now, in our last deep dive, we unpacked Chapter 13. We really got into the granular mechanics of network protection systems, looking at, how stateful inspection firewalls maintain connection tables, and how intrusion detection systems rely on heuristic and signature-based analysis to guard the perimeter.
Right.
But today, we transition to the capstone. Today's focus is Chapter 14, which is the hands-on ethical hacking final project.
I love this chapter. This is the culmination of the entire architectural buildup we've been talking about. We are finally moving from the theoretical understanding of network topologies and vulnerability categories into the literal construction and execution of a penetration test.
And to guide us through this complex deployment, I am thrilled to welcome back our resident independent industry analyst. You spend your days basically evaluating academic cybersecurity programs and cross-referencing their output with the immediate critical demands of the tech sector.
Yeah, and it is a privilege to be here analyzing this specific curriculum with you. I got to say, as an industry analyst looking at how universities prepare you for the realities of the modern workforce, I find Dr. Schuessler's Ethical Hacking and Cybersecurity Operations course particularly fascinating.
What stands out to you about it?
Well, this final project bridges a massive gap I constantly see in the industry. We have plenty of people who can read a textbook and tell you what a SQL injection is.
Right, the theory.
Exactly. But the industry, CISOs, risk management directors, technical recruiters, they are desperate for professionals who can independently provision a secure lab environment, execute the reconnaissance, isolate the vulnerability, and then actually write the executive level remediation report.
A whole package.
The whole package. This curriculum transforms academic theory into the exact, verifiable, hands-on skills that generate immediate value for an enterprise.
Okay, so let's dive right into that transformation. Before Gearhard Wagner could test the Polygon network, he had to have a completely isolated environment to run his code.
Yes.
And for you developing these skills, you don't start your journey by firing automated scanning tools at a live production web server. You have to build a crash test facility.
That's a great way to put it.
So according to our source material, the foundational requirement for this final project is architecting an isolated penetration testing lab using Oracle VirtualBox. We're integrating 3 distinct virtual machines into this environment, right? We've got the Oxygen mail server, an attacker machine running Kali Linux, and a purposefully vulnerable target called Metasploitable 2.
And the operative concept here, the absolute most important thing, is absolute isolation. I literally cannot emphasize enough why architectural isolation is the critical first step.
Why is it so crucial?
Well, when you are developing these skills, the temptation is always to look outward. You might be connected to a university network or a corporate gets Wi-Fi or even just your local ISP at home. And the thought occurs, hey, let me just run a quick network discovery scan to see what devices are communicating.
I mean, I get that impulse. It's just a scan. You aren't sending malware. You're just pinging IP addresses to see what replies. Yeah. What is the actual harm there?
The harm lies in the fundamental nature of how enterprise networks interpret unsolicited traffic.
Yeah.
So just a scan involves sending thousands of crafted TCP and UDP packets to various ports.
Right.
To a modern intrusion prevention system, an IPS, an aggressive port scan looks functionally identical to the precursor of a targeted cyber attack.
Yeah.
If you initiate that traffic on a network you do not own or lack explicit documented authorization to test, you cross a very sharp legal line.
Well, you could actually get in legal trouble.
Oh, absolutely. Right. You are performing unauthorized reconnaissance. And furthermore, fragile legacy systems like, say, an older point-of-sale terminal at a retail store or a poorly configured IoT device, they can literally crash just from the sheer volume of packets generated by a robust vulnerability scan.
Oh, wow. So you could accidentally knock a local business offline just by trying to see what operating system their router is running?
Precisely. You become a massive liability. And this is exactly why Dr. Schuessler's curriculum relies on VirtualBox and specifically dictates the use of a host-only adapter for the network configuration.
Let's focus on that host-only adapter concept for a second. I like to think of your physical computer as this massive research hospital, and your network interface card, your Wi-Fi or your Ethernet cable, is the front door to the outside world.
Okay, I like this analogy.
If you set your virtual machines to use a host-only adapter, you are essentially building a Biohazard Level 4 containment lab deep inside the basement of that hospital. You design the routing tables so that the virtual machines inside that lab have absolutely no default gateway pointing to the outside world.
They're trapped.
Exactly. They can communicate with each other, they can launch exploits at each other, and they can send data back to your host operating system, which is like the scientist taking notes. But the packets literally have no mathematical path to escape the physical hardware and hit your local Wi-Fi router.
That is a highly accurate representation of the packet routing, honestly.
Yeah.
The host-only adapter basically creates a virtual software switch inside your physical machine.
A switch that doesn't go anywhere.
Right. The VMs plug into that virtual switch, and your physical host machine plugs into that virtual switch. But that switch has no physical uplink to the actual internet. It is a closed loop, completely air-gapped network simulation.
Which is incredibly safe.
Very safe.
Yeah.
Now, architecting this containment lab, it requires the right physical foundation. The curriculum specifies that your host machine must have a minimum of 8 gigabytes of RAM to handle this environment.
Yeah, because you aren't just, opening another web browser tab. You are asking your CPU and memory controller to simultaneously run the kernel processes, the background services, and the file systems of your main operating system, plus Kali Linux, plus Metasploitable, plus the Oxygen server.
Exactly. You are multiplexing your physical hardware. If you attempt to provision all of these VMs on a system with only, say, 4 gigabytes of RAM, the hypervisor will be forced to constantly page memory blocks to your physical hard drive.
Oh, which is incredibly slow.
It's a process known as swapping or thrashing. Your entire system will suffer a catastrophic performance degradation, rendering the lab virtually unusable. It'll just crawl.
So 8 gigs is the absolute floor.
Yes. But even if your hardware is robust, there is a significant architectural conflict that frequently blocks deployment, particularly for users operating on Windows 10 or Windows 11.
Oh, I know what you're going to say.
That is the hypervisor collision with Microsoft Hyper-V.
Yes. I have seen so many aspiring IT professionals hit a brick wall right here. They install VirtualBox, they configure their VM perfectly, they click Start, and immediately get hit with a fatal execution error. I want to look under the hood here. Why do Microsoft Hyper-V and Oracle VirtualBox hate each other so much?
It really comes down to how processor architectures handle hardware-assisted virtualization. So modern CPUs from Intel and AMD, they have specific instruction sets, VTX for Intel and AMD-V for AMD.
Right, the virtualization flags.
Exactly. These instructions operate at ring 0, which is the absolute deepest, most privileged level of the processor. It allows a hypervisor to safely allocate raw CPU time to a virtual machine. Now, Microsoft Hyper-V is designed as a Type 1 hypervisor.
A bare metal hypervisor.
Bare metal, exactly. So even when running on a desktop, it fundamentally slides underneath the Windows operating system, directly interacting with the bare metal. It aggressively locks those VTX instructions for its own exclusive use.
So it just claims total domain over the virtualization capabilities of the processor?
Yes. It says, these are mine. Oracle VirtualBox, however, is a Type 2 hypervisor. It runs as an application on top of your operating system.
Like a normal program.
Right. So when VirtualBox tries to boot a VM, it reaches down to the CPU and asks for access to those VTX virtualization flags. But Hyper-V acts like a bouncer at the door and denies access.
Not on the list, buddy.
Exactly. Because Hyper-V holds the lock, VirtualBox fails to execute the virtual environment. It just crashes.
But wait, if Hyper-V is this powerful bare metal enterprise tool native to Windows, why doesn't the curriculum just have you build the lab in Hyper-V? Why are we fighting to use VirtualBox at all?
You know, that is a phenomenal operational question. While Hyper-V is an enterprise standard for production servers, VirtualBox provides a much more flexible, platform-agnostic environment for rapid penetration testing labs.
Flexible in what way?
Well, for one, VirtualBox handles USB pass-through for external wireless adapters much more smoothly, which is, critical for Wi-Fi hacking scenarios.
Oh, yeah, you need that external card.
Right. It also has broader support for a wider array of legacy and niche Linux kernels without requiring the complex integration services that Hyper-V often demands. For a dynamic, rapidly changing student lab, VirtualBox is simply more agile.
That makes perfect sense. Flexibility over raw enterprise production power for a lab environment. So how do we resolve the conflict? We have to tell Hyper-V to release the lock on the processor, right?
Yes. The curriculum provides the exact administrative command required. You must open a PowerShell terminal with elevated administrative privileges.
Got to right-click and run as administrator.
Always. You then execute a command to modify the boot configuration data. The command is bcdedit set hypervisor launch type off.
Okay, so that's bcd edit space / set space hypervisor launch type space off.
Precisely. This command tells the Windows bootloader that upon the next startup, it should not load the Hyper-V hypervisor layer beneath the operating system.
So just disables it on boot.
Right, but you must initiate a full system restart for it to take effect. Once Windows reboots, the VTX processor flags are freed up, and VirtualBox can successfully claim them to run your containment lab.
It is a critical lesson in resource allocation at the kernel level. Now, before we move on to building the VMs themselves, I want to play devil's advocate regarding the network setup for a second.
Okay, sure.
Let's imagine you are just rushing through this lab late at night. You successfully disable Hyper-V, you get VirtualBox running, but you completely ignore the instructions regarding the host-only adapter. You just gloss over it.
A classic mistake.
Right. You leave the network interface of your Kali Linux machine set to bridge mode, and you are sitting in that coffee shop we mentioned earlier. What is the mechanical reality of that mistake?
Well, if you configure a virtual machine with a bridged adapter, you are completely bypassing the software switch of that containment lab we talked about. A bridged adapter hooks directly into your physical network interface card.
So it bypasses the host OS routing?
Yep. It broadcasts a DHCP request directly to the physical router in that coffee shop, asking for its own distinct IP address on the local subnet. As far as the coffee shop's network infrastructure is concerned, your Kali Linux virtual machine is a brand new physical laptop that just walked in the door and connected to the Wi-Fi.
Oh, wow. So the isolation is entirely gone.
It is entirely compromised. So when you open your Kali terminal and initiate an aggressive NMAP port scan or launch an automated vulnerability sweep using Nessus, those packets do not stay inside your computer.
Oh, no.
They are routed out of your physical Wi-Fi antenna, across the airwaves, directly into the coffee shop's gateway router, and then blasted across their entire internal network infrastructure.
So you're basically attacking the coffee shop.
You would be actively probing the barista's point-of-sale system, the digital menu boards, and the personal devices of every patron connected to that network.
That is terrifying.
It is a catastrophic failure of operational security. It could potentially trigger automated intrusion responses from their ISP and obviously expose you to severe legal liability.
That paints a very vivid, very terrifying picture of why following network topology instructions is non-negotiable. It also applies to any existing virtual machines you have, by the way. The curriculum explicitly notes that if you have an Axygen Mail server VM from a previous lab, you must go into its settings and manually migrate its network interface to this exact same VirtualBox host-only Ethernet adapter. You have to pull everything into the same containment zone.
Absolutely. You must respect the environment before you utilize the tools.
All right, our containment facility is powered up, the processor is unlocked, and the network is air-gapped. Now, we need to gear up the attacker. This brings us to the deployment of Kali Linux 2021. But Dr. H.Schuessler's curriculum doesn't have you downloading a standard ISO file, partitioning virtual hard drives, and compiling a kernel from scratch. You are instructed to deploy Kali using an OVA file.
Yes, the OVA.
Let's unpack the architecture of an OVA. Why are we relying on this specific format?
To understand the value of an OVA, we really have to look at the traditional friction of provisioning infrastructure. If you build an operating system from a raw ISO file, you are essentially acting as a systems administrator.
Which takes forever.
It does. You must allocate the virtual disk geometry, navigate the Linux partition manager to set up your root and swap partitions, run through the package selection, configure the GRUB bootloader, and then spend hours running apt-get update to pull down all the necessary software dependencies. It is a massive time sink that distracts entirely from the actual objective of the lab.
Right. If you spend 3 hours debugging a graphical driver issue on a fresh Linux install, you aren't learning ethical hacking. You're just doing help desk work for yourself.
Precisely. So OVA stands for Open Virtualization Format Archive. It is essentially a complete, pre-configured virtual machine that has been serialized and packaged into a single deployable file.
Okay.
When Offensive Security, they're the maintainers of Kali Linux, when they build an OVA, they've already gone through the entire installation process for you. They have optimized the kernel parameters specifically for a virtualized environment. They have pre-installed and configured all the complex penetration testing tool chains so that the dependencies don't conflict.
So an OVA isn't just like an installer, it's a snapshot of a fully functioning computer frozen in time, ready to be thawed out on your machine.
Exactly. Inside the OVA package, there is an OVF descriptor file, which is basically an XML document that tells VirtualBox exactly how much RAM and how many CPU cores the machine requires, alongside the compressed virtual hard disk image itself. Utilizing an OVA is a massive optimization of your operational template.
Because it just works out of the box.
It allows you to rapidly spin up complex environments and immediately focus your cognitive energy on the attack methodology rather than, infrastructure troubleshooting.
That efficiency is vital in a professional setting. Time is money, right? So how do you actually execute this deployment in VirtualBox?
The deployment workflow is incredibly streamlined. You navigate to the official Kali Linux infrastructure page, specifically seeking out the pre-built virtual machines repository. You must download the 64-bit VirtualBox specific version of the OVA file to your host machine.
Make sure it says VirtualBox, not VMware.
Good point, yes.
Okay.
Once that substantial file is downloaded, you do not use the new machine wizard in VirtualBox.
Yeah.
Instead, you utilize the import appliance function found under the file menu.
You just point VirtualBox to the OVA, it reads that XML descriptor file you mentioned, and it automatically configures the virtual hardware profile to match what the Kali developers intended.
That is correct. You review the hardware allocation, accept the software licensing agreements, and VirtualBox executes the extraction and translation process. Within minutes, a fully optimized Kali Linux environment appears in your hypervisor inventory.
Beautiful.
However, and this is a big however, before you even think about powering it on, you must apply the networking constraints we discussed.
Right back to the Biohazard protocol. You right-click the newly imported Kali VM, navigate to the network settings, and change the adapter attachment from its default, which is often NAT or bridged to the host-only adapter, ensuring it resides on the exact same virtual software switch as your Oxygen server.
Exactly. If you neglect that configuration, your attacker machine will be functionally blind. It will have no route to communicate with the target systems in your lab.
Okay, the attacker is geared up and locked in the containment zone. Now we need to architect the target. In this curriculum, the primary target is a system engineered by the security firm Rapid7, known as Metasploitable 2.
Metasploitable.
This represents a fascinating paradigm shift, I think. In IT, we spend our entire careers trying to harden systems, remove technical debt, and enforce complex password policies. Why would a highly respected security company intentionally engineer and distribute an operating system that is fundamentally broken?
It really speaks to the absolute necessity of applied practice in cybersecurity education. Metasploitable 2 is a masterpiece of engineered vulnerability.
A masterpiece of vulnerability. I like that.
You cannot train an incident responder or a penetration tester exclusively on theoretical models of secure systems. They need a sandbox where they can safely analyze how exploits detonate, how payloads execute in memory, and how misconfigurations can be chained together to achieve total system compromise.
It's the digital equivalent of a ballistics dummy. You have to shoot it to understand how the armor fails.
That is an apt comparison. So Metasploitable 2 is built on an older Ubuntu Linux framework, but it has been systematically stripped of modern defensive mechanisms, like address space layout randomization.
Okay, so it's defenseless.
It is loaded with legacy, unpatched services. We're talking vulnerable versions of Samba, outdated Apache web servers, and inherently insecure protocols like Telnet and pure FTP. It provides a target-rich environment for you to test your reconnaissance and exploitation skills without the risk of damaging a production asset or violating authorization boundaries.
But the deployment methodology for Metasploitable 2 diverges from Kali. The textbook explicitly notes that Metasploitable 2 is distributed as a ZIP archive containing a VMDK file, not an OVA. How does architecting a VM around a VMDK differ from importing an appliance?
Well, if importing an OVA is like having a fully assembled server delivered to your data center rack, using a VMDK is like being handed a hard drive and being told to build a server around it.
Okay, that makes sense.
VMDK stands for Virtual Machine Disk. It is simply the raw, virtualized storage medium containing the operating system and file structure. Because there is no OVF descriptor file to tell VirtualBox how to build a machine, you must manually provision the virtual motherboard, the CPU architecture, and the memory controller, and then explicitly attach the VMDK as the primary storage device.
Let's walk through that architectural process for you guys listening. Once you extract the downloaded ZIP file, you locate the metasploitable.vmdk file.
Right, and you then initiate the new virtual machine wizard in VirtualBox. You manually define the operating system profile, designating it as a Linux kernel, specifically the other Linux 64-bit version. Next, you allocate the RAM. The curriculum suggests 512 megabytes.
512 megabytes. Wait, my web browser uses more than that just sitting idle. Why is the allocation so low?
Because Metasploitable 2 is engineered as a headless server environment. It does not load a graphical user interface or a desktop environment.
Ah, no GUI.
Right. It boots purely to a command line terminal. A legacy Linux kernel running background daemon services requires exceptionally little memory overhead. It is a highly efficient, lightweight target.
After allocating the memory, you reach the storage configuration. Instead of instructing VirtualBox to dynamically allocate a new, empty virtual hard disk, you select the option to use an existing virtual hard disk file. You navigate your host machine's file system, locate that extracted metasploitable.vmdk file, and attach it to the virtual IDE or SATA controller.
Yep. And then you finalize the creation, immediately enter the network settings to bind it to the host-only adapter again, Biohazard protocol, and then initiate a normal start.
And what happens then?
The system will execute its boot sequence, and you will see the Linux kernel initializing, mounting the file systems, and starting those vulnerable background services, culminating in a simple text-based login prompt.
The curriculum provides the default credentials, which are the username is mspadmin and the password is the exact same string mspadmin.
Extremely secure.
Right. Once authenticated, you execute the ifconfig command. This queries the Linux kernel for the network interface configuration, allowing you to identify the specific IP address dynamically assigned to the each interface of the Metasploitable machine.
Yes.
Because your Kali attacker needs this IP address to actually target its scans. Now, I have to pause here. We just authenticated to a server using mspadmin as both the username and the password. It feels comically negligent. Is this just an academic exaggeration for the sake of an easy lab, or does this actually reflect reality?
Sadly, it is a stark, terrifying reflection of enterprise reality. In my analysis of post-incident reports from massive data breaches, the exploitation of default or hard-coded credentials remains a dominant vector for initial access.
You mean companies are actually deploying hardware into production environments without changing the password from admin, like in the real world?
Constantly. We see enterprise-grade IoT security cameras deployed with admin and 1, 2, 3, 4, 5. We see massive database instances spun up by DevOps engineers who intend to change the root password later, but they just forget.
Oh, wow.
We see network switches operating on default vendor SNMP community strings. When you log into Metasploitable using mspadmin, you are directly simulating the exact operational failure that allows ransomware operators to bypass million-dollar firewall arrays. You are learning that the most sophisticated technical exploit is often completely unnecessary when an organization fails at basic credential hygiene.
That is such a sobering reality check on the state of industry security. Okay, so our architecture is complete. The host-only lab is sealed, Kali Linux is armed, and Metasploitable 2 is actively broadcasting its vulnerable services on the internal subnet.
We're ready to go.
It is time to transition from engineering the environment to executing the attack methodology. We are looking at the Reconnaissance arsenal. The source material emphasizes a specific suite of command line tools: NMAP, Netcat, Wget, and NM4 Linux.
The classics.
Let's start with NMAP, the network mapper. It is universally revered in the cybersecurity community. How does NMAP actually map a network without having any prior knowledge of its topology?
Think of NMAP not just as a scanner, but as a highly sophisticated sonar system operating at the transport layer of the OSI model. When you initiate an NMAP scan against a target IP address, it doesn't just ask the system what it is doing. It systematically crafts and transmits specific TCP and UDP packets to all 65,535 possible communication ports on that machine and meticulously analyzes the cryptographic flags in the packets that the target sends back.
I want to break down the mechanics of that interaction for a second.
Yeah.
Let's say I launch a basic TCP SYN scan from Kali against Metasploitable. What is actually happening on the wire?
Okay, so a SYN scan, often called a stealth or half-open scan, exploits the fundamental mechanics of the TCP three-way handshake. When NMAP targets port 80, which is a standard port for unencrypted HTTP web traffic, it sends a packet with the SYN or synchronized flag set. It's essentially saying, "Hi, I would like to initiate a connection." If a web server application is actively listening on that port, the target machine's operating system responds by sending back a packet with both the SYN and ACK, or acknowledge, flag set. It says, "I acknowledge your request, and I am ready to connect."
In a normal network interaction, like if I was just browsing the web, my machine would then send a final ACK packet to complete the handshake, establishing the connection, and then we'd start sending web data back and forth.
Exactly. But NMAP doesn't want to establish a connection. It just wants to know if the door is open. So the millisecond NMAP receives that SYN ACK response. It immediately tears down the connection by transmitting an RST or reset packet It abandons the handshake.
It just walks away. Why do it that way? Why not just complete the handshake?
Because by never completing the full TCP connection, the application layer on the target system, the web server software itself, often never logs the interaction.
Ah, so it's stealthy.
Exactly. The interaction is handled entirely by the lower-level operating system kernel. It provides the attacker with a comprehensive map of every open port and available service while minimizing their footprint in the target's application logs. NMAP processes these millions of packet interactions and outputs a clean, readable list. Port 21 FTP is open, port 22 SSH is open, port 80 HTTP is open.
So NMAP provides the structural blueprint of the target. It tells me that there is a web server operating on port 80, but knowing a web server exists isn't enough to launch an exploit.
No, it's just the first step.
I need to know exactly what web server it is. Is it Microsoft ISARN? Is it Apache? Is it Nginx? This is where the curriculum introduces Netcat, often abbreviated as NZES. How do we use Netcat to transition from port discovery to precise service identification?
Netcat is universally referred to as the Swiss Army knife of TCP/IP networking. It's a remarkably pure utility. It simply reads and writes raw byte streams across network connections. It doesn't care about protocols or formatting at all. When NMAP reveals that port 80 is open, you can utilize Netcat to connect directly to that port and manually send raw HTTP application layer commands.
So instead of using a web browser that formats everything nicely and handles the background stuff, I use Netcat to establish a raw socket connection, and I manually type an HTTP request, like JA HTTP 1.0, and hit enter.
Precisely. Because you are communicating at the raw protocol level, the target web server will respond by sending back its raw HTTP headers before it sends the actual HTML code of the website. Embedded within those headers is often a server field. This is known as the banner.
And what does that banner say?
The server banner might explicitly declare, server, Apache 2.2.8 Ubuntu.
That is the gold mine right there.
It is the critical pivot point of an attack. You have transitioned from knowing a port is simply open to knowing the exact vendor, the exact software daemon, and the exact version number running on that port. As an ethical hacker, you take that precise version number and query vulnerability databases. If Apache 2.2.8 is known to be vulnerable to a specific buffer overflow or remote code execution exploit, your path to compromising the system is now completely clear. Netcat facilitates that manual banner grabbing.
I really see the power of that manual interaction. Now, the curriculum also highlights Wget. Most people know Wget as a simple Linux command line utility for downloading files. How does a file downloader function as a reconnaissance tool?
It functions as a tool for asynchronous silent analysis. If you navigate to the target's web server using a graphical browser like Firefox on your Kali machine, your browser executes JavaScript, loads tracking pixels, dynamically requests hundreds of resources, and leaves a massive continuous footprint in the server's access logs detailing your user agent, operating system, and browsing behavior.
It is a very noisy way to analyze a target.
Very noisy. But with Wget, you can execute a single command to recursively mirror the entire directory structure of the website locally to your Kali hard drive.
Oh, wow.
Exactly. You pull down the raw HTML, CSS, and JavaScript files in one swift action. You can even spoof your user agent string so the server thinks a harmless search engine bot is requesting the files. Once the site architecture is downloaded to your local machine, you sever the connection.
You go offline.
Right. You can then spend hours utilizing tools like grep to parse through the raw source code offline. You are hunting for hidden developer comments, hard-coded API keys, exposed database connection strings, or hidden administrative directories like a backup or .git folder that the administrators forgot to restrict. You are mapping the application logic without actively engaging the target server anymore.
It's basically reconnaissance by exfiltration. You steal the blueprints and study them back at base.
That's exactly it.
Now, rounding out this manual arsenal is a highly specialized tool called enum4linux. Given the name, I assume this isn't for web servers. What specific protocol is this tool attacking?
enum4linux is precision engineered to extract information via the server message block, or SMB protocol, which is the foundational technology for file and printer sharing in Windows, and is implemented in Linux via the Samba suite. SMB is notoriously chatty and complex. enum4linux exploits legacy mechanisms within this protocol, specifically the concept of null sessions.
I've heard that term. What exactly is a null session?
Historically, for network components to discover each other easily, the SMB protocol allowed unauthenticated connections to a hidden inter-process communication share known as IPCS. If a system like our Metasploitable target running an outdated Samba daemon is misconfigured to allow null sessions, enum4 Linux connects without a valid username or password.
And once connected without a password, what can it actually extract?
An astonishing amount of administrative data. It queries the system's internal security identifier, or SID, structure. It can extract a complete list of local user accounts on the machine, the entire password policy revealing minimum password lengths and complexity requirements, the system's exact operating system architecture, and a map of all available network file shares.
That is insane. So without ever successfully logging in, without guessing a single password, enum4 Linux forces the system to hand over the complete employee directory, the map of the file server, and the rules for how passwords are constructed.
Yes, it gives you everything you need.
You can then feed that list of valid usernames directly into a brute force attack tool, exponentially increasing your chances of a successful compromise because you are no longer guessing who exists on the system, you just have the list.
It is the ultimate manifestation of information leverage. Now, I want to address a critical pedagogical point regarding Dr. Schuessler's curriculum here.
Please do.
In the modern commercial market, there are incredibly sophisticated multi-$1,000 vulnerability scanners with beautiful graphical interfaces that automate all of this. You just type in an IP address, click scan, and it does everything we just discussed. So why force students to utilize text-based command line tools like Netcat and enum4 Linux?
I would assume it's because clicking a button doesn't teach you how the engine works. If the automated scanner fails or if it encounters a completely novel network configuration it doesn't recognize, the operator who only knows how to click scan is completely paralyzed.
Exactly. In the industry, we differentiate between script kiddies, individuals who rely entirely on automated tools without understanding the underlying mechanics, and highly capable cybersecurity engineers. A professional incident responder needs to understand the exact structure of an HTTP GET request, the mechanics of a TCP three-way handshake, and the syntax of an SMB null session.
The fundamentals.
Right. When the automated tools fail, or when an advanced persistent threat actor custom builds malware that evades commercial signatures, the professional drops down to the command line and manually enumerates the environment. The command line is where true technical mastery resides. The manual tools are the foundation.
You really have to master the manual transmission before you can optimize the automatic. However, once you intimately understand the underlying protocols, manually grabbing banners for every single port on a subnet with 1,000 machines is, well, inefficient.
Oh, completely inefficient at scale.
This is where the curriculum pivots from manual targeted reconnaissance to broad spectrum automated vulnerability analysis. We move to the heavy artillery, Nessus Essentials.
If NMAP and Netcat are a scalpel used for precise, localized extraction, Nessus is a magnetic resonance imaging machine. It is an industry-standard commercial-grade vulnerability scanner engineered by Tenable. The curriculum outlines a highly structured two-phase operational methodology for deploying Nessus within the containment lab.
Let's talk about phase one, which is host discovery. The source material explicitly defines a target parameter utilizing classless interdomain routing, or CIDR notation. It gives the example of targeting 192.168.56.024. Let's analyze that 24 suffix for a second. How does Nessus interpret that parameter?
That 24 subnet mask is a critical configuration parameter. It instructs the Nessus scanning engine on the exact boundaries of its operational theater. In binary, an IPv4 address is 32 bits long. A 24 subnet mask dictates that the first 24 bits represent the fixed network address, leaving the remaining 8 bits available for individual host addresses.
Okay, and mathematically 2 to the power of 8 yields 256.
Precisely. So by appending 24, you are telling Nessus, do not scan a single machine. I want you to sweep this entire contiguous block of 256 possible IP addresses on the host-only virtual switch.
It's sweeping the whole neighborhood, basically.
Exactly. Nessus leverages ARP broadcasts and ICMP echo requests to sweep that entire subnet. It maps the topography of the containment lab, identifying exactly which IP addresses have active virtual machines responding on them. It defines the attack surface.
Once the active hosts are identified, we transition to phase 2, deep scanning. The curriculum directs you to execute a basic network scan and a web application test scan against specific targets like the Metasploitable VM.
This is where Nessus transitions from discovery to active exploitation analysis.
Yeah.
Nessus operates utilizing a massive database of plugins.
What exactly is a plugin in this context?
Each plugin is essentially a highly specific script written in the Nessus Attack Scripting Language, or NASL, designed to interrogate a system for a single, specific flaw. Nessus hurls thousands of these customized packets at the target, analyzing the responses to determine if a vulnerable condition exists.
Like checking a massive checklist.
Right. It checks for missing security patches, dangerous default configurations, weak cryptographic ciphers, and known buffer overflow vulnerabilities.
And when the scan completes, it aggregates all of this complex data into an incredibly intuitive dashboard. You are presented with analytical pie charts, categorizing the identified vulnerabilities by a severity scale. Info, low, medium, high, and critical.
The colors really jump out at you.
They do. I can tell you from experience, when you analyze a Nessus report and see a massive bright red segment labeled critical, your adrenaline spikes. It means the system is fundamentally compromised. But here is the critical pivot point in the curriculum. The scanner tells you the system is broken. It gives you a red chart. But how do you, as an ethical hacker, translate that red chart into a mechanical understanding of the exploit and ultimately a strategy for remediation?
That translation is the core competency of a cybersecurity analyst. Nessus bridges that gap by correlating every identified vulnerability with an alphanumeric identifier known as a CVE, Common Vulnerabilities and Exposures.
The CVE system is maintained by the MITRE Corporation, right? Think of it as a globally standardized, highly indexed encyclopedia documenting every publicly disclosed software flaw and hardware vulnerability in existence.
Exactly. When Nessus flags a critical vulnerability on your Metasploitable target, it doesn't just say Samba is bad. It outputs a specific reference, such as CVE 2007-23447, which is a notorious remote command injection vulnerability in Samba. The curriculum explicitly directs you to take that CVE identifier and query it within the NIST National Vulnerability Database, the NVD.
When you query the NVD, you aren't just looking at a summary, you are looking at the foundational architecture of the risk.
You're accessing the definitive intelligence regarding that flaw. The NVD provides the Common Vulnerability Scoring System, or CVSS vector, mathematically breaking down the severity based on whether the attack requires local access, or it can be executed over the network, how complex the exploit is, and whether it requires the victim to interact.
It gets really granular.
Extremely. Crucially, the NVD provides extensive documentation on the exact mechanical failure in the software's code that allows the exploit to function, lists at every specific version of the software affected by the flaw, and provides direct links to the vendor's official security advisories and patch repositories.
It's like Nessus acts as the diagnostic instrument pointing out the symptom, and the CVE database provides the comprehensive pathology of the disease and the exact pharmaceutical formula required to cure it.
That's a brilliant analogy. And this methodology is not merely an academic exercise either. The source material explicitly correlates these virtual machine lab procedures with the core objectives of industry standard certifications like CompTIA Security Plus and Pentest Plus DOS.
Which are huge for getting hired.
Oh, absolutely. By manually deploying these scanners, interpreting complex CVSS metrics, and utilizing the CVE database for actionable intelligence, you are acquiring the exact verifiable competencies that credentialing bodies and corporate hiring managers demand. You are building a portfolio of practical capability.
Which brings us to the ultimate realization of that capability. You have successfully architected the containment lab. You have utilized manual command line utilities to enumerate the network. You have deployed Nessus to identify critical CVEs. You possess a profound technical understanding of the vulnerabilities compromising the target architecture.
The fun part is over.
Right. The technical execution of the penetration test is complete, but the professional engagement is not. We have arrived at the final and arguably most critical phase of the curriculum, translating hacks into value through the penetration testing report.
This is a fundamental paradigm shift that many highly technical individuals struggle to grasp. You can possess the most profound understanding of By86 assembly language. You can develop custom zero-day exploits that bypass enterprise-grade endpoint detection and response systems. But
there's always a but.
But if you cannot articulate the mechanics of that vulnerability, translate its technical severity into business risk, and provide a clear executable roadmap for remediation in a structured document, your technical brilliance generates zero return on investment for the organization.
The technical hacking is merely the data collection phase. The report is the actual product the business is purchasing.
Yeah, exactly. The textbook outlines a highly specific, standardized technical report format. This format is the universal language of the cybersecurity industry because it is engineered to communicate effectively with vastly different organizational audiences simultaneously. Let's deconstruct the architecture of this document. It invariably begins with the executive summary.
The executive summary is not written for the systems engineers. It is written for the Chief Executive Officer, Board of Directors, and the Chief Information Security Officer.
The people holding the purse string.
Right. They do not have the time, nor often the technical background, to understand the intricacies of a TCP SYN scan or the syntax of an SMB null session. They are concerned with risk management, legal liability, and resource allocation.
The executive summary must translate technical metrics into business reality in plain, authoritative language. It concisely states the objective of the engagement, provides a high-level overview of the systemic risk posture. For example, the internal network is highly susceptible to remote ransomware deployment due to unpatched legacy services, and summarizes the core strategic recommendations required to mitigate that risk, all within a few paragraphs.
Following the summary, the report defines the introduction and scope. This is where you establish the legal and operational boundaries of the engagement.
Scope definition is critical for liability protection. You must explicitly document what IP subnets, domains, and specific applications were authorized for testing. Just as importantly, you must document what was explicitly excluded.
Why is documenting exclusions so important?
Well, if the rules of engagement dictated that social engineering and phishing were out of scope, and then a week after your test, an employee compromises the network by clicking a malicious email link, the scope section proves that the vector was outside your contractual mandate. You're covered.
That makes total sense. Once the boundaries are established, we enter the core of the document, the detail section. If the executive summary is for the CEO, the detail section is for the network architects and system administrators who actually have to apply the patches. This is where you lay out the forensic evidence.
The curriculum emphasizes the rigorous structural formatting required here. You do not write a stream of consciousness narrative. You employ a strict numerical hierarchy. 4.1 for the first major finding, perhaps detailing the results of the NMAP reconnaissance. 4.2 for the vulnerability analysis of the web server. 4.2.1 for a specific critical CVE discovered on that server.
Keeping it organized.
Yes. This structured approach allows an engineer to immediately navigate to the precise technical data they need. This section houses the raw HTTP banners extracted via Netcat, the specific plugin outputs from Nessus, and the exact commands you executed to achieve compromise.
It provides the reproducible proof of the vulnerability. Following the detailed evidence, you provide a summary segment which synthesizes those granular findings into an assessment of the overall architectural integrity of the system. Are these isolated misconfigurations, or do they indicate a systemic failure in the organization's patch management lifecycle? But the true value of the report culminates in the recommendation section.
If the details section is the clinical diagnosis of the pathology, the recommendation section is the precise surgical prescription. You cannot simply point out that a server is vulnerable to CVE 2007-2447. You must leverage the intelligence gathered from the NVD and provide actionable, prioritized remediation strategies.
Give them the fix.
Exactly. Do they need to upgrade the Samba daemon to version 3.0? Do they need to modify a specific configuration file to disable null sessions? Do they need to segment that legacy server behind an internal firewall? Your recommendations define the operational roadmap for securing the enterprise.
The report concludes with a synthesis of the objective, findings, and recommendations, followed by the annexes. Annex A for references, Annex B for the myriad of acronyms used in the IT industry, and Annex C for the detailed results from tools. Annex C is essentially the raw data dump, the unedited NMAP logs, and the complete Nessus export files, providing absolute transparency and allowing any external auditor to verify the integrity of your findings. Now, I want to highlight a specific element from the instructor's manual regarding this report, the standard writing rubric.
Yes. It assesses content, organization and clarity, research and citations, and grammar and spelling.
It is incredibly easy for you, as someone deeply passionate about writing code and executing exploits, to view a grammar and spelling rubric as like irrelevant academic busy work. You might think, I'm a cybersecurity operator, not a technical copywriter. Why does pristine grammar fundamentally matter in this field?
Because in the corporate hierarchy, your technical competence is judged entirely through the lens of your professional communication.
Really? Entirely?
I mean, practically speaking, yes. If you present a penetration testing report to a risk management committee, and the document suffers from structural disorganization, relies on inconsistent formatting, and is riddled with typographical errors, the executives reading it will make an immediate subconscious correlation.
They'll judge the work by the cover.
They will assume that if you lack the discipline to proofread your sentences, you lack the precision required to safely execute complex exploits on their production network. sloppy communication destroys technical credibility. Mastery of grammar, clarity, and professional formatting is not an academic hurdle. It is the prerequisite for influencing C-suite executives, securing remediation budgets, and accelerating your career trajectory.
Credibility is the currency of the industry, which, brings us full circle back to the incredible narrative of Gearhard Wagner and the Polygon blockchain that we explored at the very beginning of this deep dive.
Wagner did not receive a $2 million bounty simply because his technical intellect allowed him to identify a cryptographic timing mismatch in a smart contract.
Right, finding it wasn't enough.
He received that unprecedented payout because he possessed the professional capability to document that highly complex vulnerability, construct a flawless, reproducible proof of concept, and deliver a comprehensive vulnerability report that allowed Polygon's distributed engineering team to immediately comprehend the risk and deploy a patch before a malicious syndicate could weaponize the exploit.
His ability to seamlessly translate a highly abstract technical exploit into a clear, actionable professional report was literally valued at millions of dollars. The technical discovery was the prerequisite. The communication was the deliverable.
That is the ultimate synthesis of Dr. Schuessler's final project. The capability to map a network, isolate a CVE, and detonate an exploit is a powerful technical skill. But the ability to contextualize that vulnerability, articulate its systemic impact, and author the authoritative roadmap for remediation is what defines a highly compensated, strategically vital cybersecurity professional.
What a phenomenal architectural journey this has been. Let's execute a final recap of the operational pipeline we just constructed. We initiated the engagement by architecting a completely isolated, biohazard-level containment lab utilizing Oracle VirtualBox, ensuring we neutralized the hypervisor conflict with Microsoft Hyper-V to protect the integrity of the physical network.
We optimized our deployment by importing a pre-configured Kali Linux OVA, equipping our attacker environment rapidly, and we manually provisioned our target, Metasploitable 2, utilizing a raw VMDK file, intentionally exposing a landscape of legacy vulnerabilities and default credentials to analyze.
We then initiated the reconnaissance phase, eschewing automated interfaces to utilize fundamental command line utilities. We deployed NMAP to conduct stealth TCP SYN scans, leveraged Netcat to extract raw application banners, utilized Wget for silent HTML exfiltration, and weaponized enum4 Linux to extract critical administrative intelligence via SMB null sessions, fundamentally separating our methodology from that of automated script kiddies.
We scaled our analysis by deploying Nessus Essentials, executing broad-spectrum vulnerability sweeps across our 24 subnet, correlating the identified flaws with the global CVE database, and extracting actionable remediation intelligence directly from the NIST National Vulnerability Database.
Finally, we translated that raw cryptographic and network data into a structured, executive-ready penetration testing report, mastering the formatting and clarity required to communicate technical risk to corporate leadership. We bridged the gap between academic theory and enterprise value, but before we sign off, we must emphasize a vital, non-negotiable protocol from the curriculum, the white hat reminder.
Yes. The methodologies and tools you develop in this curriculum, network enumeration, vulnerability identification, and exploit execution, are extraordinarily powerful. They manipulate the fundamental architecture of digital communication. And with that power comes absolute responsibility.
100%.
The source material dictates extreme caution. Do not download unverified compiled executables or exploit scripts from unknown repositories while researching CVEs. Rely on vetted sources, textual analysis, and safe demonstration environments.
Most importantly, you must always maintain your ethical parameters. You must wear the white hat. Never, under any circumstances, aim these scanning engines or reconnaissance tools at a network, a server, or an application that resides outside of your isolated VirtualBox containment lab unless you possess explicit, written, and legally binding authorization from the owner of that infrastructure.
The distinction between a highly respected ethical hacker and a malicious threat actor facing severe legal prosecution is entirely defined by authorization and target selection. Keep the lab environment completely isolated, rigorously respect the legal boundaries, and utilize this profound knowledge to secure, fortify, and build resilient systems, never to disrupt or destroy.
Thank you so much for joining us on this deep dive and for dedicating your time to this entire 14-part series. It has been an absolute masterclass in network defense architecture and ethical hacking methodology. Please take a moment right now to like, subscribe, and share this series. Getting this complex technical information distributed is how we systematically build a more resilient and secure global digital infrastructure. And don't forget to check the description below for access to additional resources that will help you continuously educate yourself and refine your operational capabilities.
In the cybersecurity domain, the threat landscape evolves daily. The commitment to continuous, rigorous learning is the only mechanism for maintaining operational superiority.
It is a lifelong pursuit. If you found value in this series and are driven to continue expanding your technical skill set, I strongly encourage you to review the channel for other content. We have a highly detailed digital forensics podcast series if you want to understand the mechanics of investigating and reverse engineering cybercrimes after a breach has occurred, and a networked and system security podcast series that dives even deeper into the architecture of enterprise-scale defense systems. Thank you truly for listening and for dedicating your intellectual energy to mastering this critical material. Encourage your peers to check the channel for other podcasts, playlists, and videos that might spark their passion for this incredibly dynamic field.
It has been a distinct privilege to analyze the mechanics of this curriculum with you and to highlight how these foundational skills translate directly into immense professional value within the tech sector.
I want to leave you with one final, deeply reflective thought. Mentally visualize the network architecture at your own workplace, your corporate office, or your university right now. Consider the core routers, the legacy file servers, the network printers, the IoT devices, and the thousands of endpoints connected to that infrastructure. If an authorized engineering team deployed a fully updated Nessus scanner against that entire subnet tomorrow morning, how many critical red slices do you honestly think would illuminate that executive dashboard?
Master the attack, fortify the defense.
Until next time, keep your hands on the keys and your network secure.